Thank you to Maziar for arranging this talk, but also the talk that's happening next week. Constantine Burnley will be taking. So this is kind of preparation for that, and it's based on a paper. Maybe after your talk, you can put the link to the paper in the chat.
Sounds good.
Okay.
Okay, thank you for the opportunity. I'll be talking about this recent paper of Contreras, Candle, Menev, and Burnley on combinatorial quantum field theory on graphs. Okay, so I have a vested interest in discretizing field theories and quantum field theories, especially when there is a metric on a spacetime. So this happens a lot in physics. For example, in Yang-Mills theory, you have a metric on a spacetime. Today, we're going to look at a simpler model, which is called scalar field theory. And we have a metric. So this paper provides us with a toy model for a discrete field theory where there is a metric. So my goal is to give you a functorial definition of QFT. Well, this has been done in the general formalism in general, and is referred to as Atiyah-Siegel axioms, or the functorial approach to quantum field theory. But I want to do this for this particular case of graphs. So on graphs, and I would like to use this functor to tell you about how to glue geometric information on smaller pieces of graph to get the corresponding geometric information on the bigger piece, on the bigger graph. So by geometric information, I'm referring to the graph Laplacian. Okay, so we know that Laplacians in general encode geometric information. That's why I'm calling it. So use this to get gluing formulas for the determinant of Laplacians, so graph Laplacians, and also Green's functions. Okay, so that's what we're going to be working towards. So first, I have to tell you about our spacetime, which is a graph. Okay, so it's a graph X, and we are thinking of graphs as a one-dimensional complex. So you have 0 cochains and 1 cochains. You have the coboundary map. Okay, and I will also put a metric on my cochains. So put a metric K is 0 or 1. And using that, I get an adjoint to this coboundary operator. So to this coboundary, I get an adjoint using this metric, and I will denote that by d star as usual. Okay, and by composing these two maps, I get an operator, which is denoted by delta, suggestively, and this is this goes. So it's defined to be this guy, which goes from C0 to itself. Thank you. So, okay, so this is called the graph Laplacian. there is another way of writing the graph Laplacian in a, oh, sorry, I forgot to tell you what exactly this metric is. So I would like it to be the standard L2 inner product. Okay, so this is different color. Standard L2 inner product. So in particular, I have a distinguished basis for C0 and C1 coming from the vertices and the edges, and the inner product of, for example, a cochain that is 1 on vertex 1 or vertex I and 1 on vertex j. So the inner product is going to be 1 if I is the same as j, and it's going to be 0 otherwise. And similarly, you define it for edges. Yes.
So what is C naught of x? You're just considering this like it's a finite set of points, and then you're taking function type.
Yes. Yes. So these are real valued functions.
There's no continuity or differentiability.
No, real valued functions on vertices.
And then what is C1 of x is real valued function on edges.
And that's C1.
Okay, sorry.
Okay. And so thank you. So in particular, you can identify C0 by R to the dimension of the number of vertices that X has. Okay, but let me tell you the other formulation, the other way of writing the graph Laplacian for a simple graph. So you can also write it as the difference of two matrices in this distinguished basis that I was talking about. So this first one is the degree matrix. And what it has is that, so for example, for this graph X, you put the degree of each vertex on the diagonal. So this one is going to be 1, 1. Okay, and A is the adjacency matrix. And that encodes which vertices are connected to which. Okay, so here, AX is, well, vertex 1 is not connected to itself, so it's 0. It's connected to vertex 2, so it's 1. Similarly, this way. And by doing this, you see that the graph Laplacian is actually symmetric. So it's a symmetric matrix. Okay. One more thing that we're gonna do for our theory is that I have to add a new parameter, and it's called mass. Okay, so I want to define this operator, the kinetic. It's called the kinetic operator, and hopefully we'll see why. And this is just defined to be this. So m is a fixed positive number. Okay, it's called the mass. So this is going to be my main operator that I'm going to be looking at. Okay, so now I'm in a position to define the classical field theory. So it's a classical field theory. And, well, it's a field theory. My space of fields, for a field theory, I have to tell you what the space of fields is. And in this case, I'm going to let it be C0, just the functions on vertices. Okay, and because of this choice, it's called a scalar field theory. Okay, and the other piece of information I need to tell you in order to define a field theory, it's an action functional. Okay, so it goes from fx to r. And here, well, for a particular field, so this is an element in here, you can write it. So usually people write it as a quadratic term plus higher order terms. I am not going to consider the higher order terms in this talk. It is considered in the paper, but so the quadratic term uses this operator that I defined up here, the kinetic operator. Okay. And because of this choice that I just made, that I'm not considering other things here, other polynomials in phi, this is called a free theory. So it doesn't have, this part is called interaction. It doesn't have that part, right? And the other thing is that because I added in this mass, it's called a massive field theory. So it's a massive, somewhere add a massive. Okay, so it's a massive field theory. Okay. Now I would like to move towards quantum theory. So I have to do quantization. And for that, because I'm using Feynman path integral formalism, I would need to tell you, I would have to give you a measure on my space of fields. Okay, so note that because this space of fields is finite dimensional, a lot of the difficulties that are usually present in a field theory in this quantization, in this path integral formalism goes away. So in particular, I can define a measure. So let me give you measure on fx. And I will use this notation throughout the talk. And so this is defined to be this product. And I'll tell you what I mean by this, but it's a normalized, it's basically a normalized Euclidean measure on r to the vx, right? On fx. So this is, and v is in vx. Okay. So for example, for that simple graph, for this guy, fx can be identified with r2. And d phi is going to be, well, I'm picking coordinates, dx1, dx2 over 2 pi h bar. Okay. And so this thing called the partition function contains pretty much all the information that you need about your theory. So it's defined to be x. So you integrate over your space of fields using that measure that I just gave you, a particular weighting of your fields. So this is Sx. Okay, so Zx is just a number in this case. Okay, and the idea is that you are looking at the configuration space at the field space at the space of fields, and you're weighting each field differently, and you're taking a superposition of them. Moreover, you're weighting those that are close to the critical locus of this functional higher than those that are not near the critical locus. Okay. The other thing that's, okay, so physicists are interested in doing measurements, and for that, measurements in this formalism is denoted by this. So if you have, I guess, point operators, right? These are, for us, these are just fields at different vertices. Okay, so on.
Is a function of h bar and n.
Mm-hmm.
Usually x. I mean, you have subscript X, but it's also a function of,
That's true. Yeah, you have these two parameters. Okay, and this is but now you put
I guess I want to make that point. It's just that when people say that all of the information is contained in the partition function,
Mhm.
it's really not. If it was, it wouldn't be true if it was just numbered. The fact that it's a function of the parameters.
I
means
see.
that you can differentiate with respect to those parameters, and you can extract a lot of information. It's
Right.
It's a generating function, and so the variables for which it is a generating function are important. Otherwise, it doesn't really contain much information at all.
Yes. Yes, or you could add in a source somehow. Okay, so right, and then the rest of this integral is putting in these you can think of them as coordinate functions. Okay, and again you integrate over fx. Okay, so this is called the correlation function, or here endpoint correlation function, because there are endpoints.
So it's a correlation function associated to these observables. Like the observables are evaluation of the field
At a point,
That's
right.
the evaluation of the field at V2, etc. These are evaluations of the fields at points. And because the field is a scalar field, it has a numerical result. So we can have the correlation.
Okay, so now we are moving towards defining what we mean by a quantum field theory in this functorial, from this functorial point of view.
Excuse me.
Yes.
Should there be some imaginary unit somewhere?
Yeah, so this is right. So yes, you could have an I in here, but what we are looking at is the Wick rotated theory.
Okay.
So that's one way of thinking about it, or you could view this as a statistical mechanical model. But it's better to think in terms of the Wick rotation because I'm saying quantum field theory a lot. Okay. So this functor that I've been talking about, the QFT functor, it goes from some cobordism category in general. So here we have the category of graph cobordisms. I have to tell you what that is. To some linear category, and here we are picking, and this is usual, we take the category of Hilbert spaces. So objects here are Hilbert spaces. And morphisms are linear maps. Linear maps, you want them to be bounded in some sense. Okay, and the objects here are graphs. Okay, so let me make myself more space. So it's Y, which is a graph. This is an example of an object. We call the object's boundaries. So this is called a boundary graph or an end. So these are different words used here. And a morphism, importantly, in this category, it's also a graph. So the morphism X goes from, say, what do I write here? Y in to Y out. It's a graph X that contains Y in and Y out as disjoint subgraphs. So these are disjoint subgraphs. Okay, and composition of morphisms on this side is taking unions of graphs with identification of these boundary graphs. So if you have y1, so this is one morphism between this guy and this guy. If you compose it with then this is just y1 to y3. And here I put x, where by x I mean x prime union x double prime over this. So it's a gluing of these two graphs over this common subboundary y2. Okay. And let me see. So I want to now tell you what this functor actually is. Yes.
Are the graphs just like anything? Are they connected? Do they have to be connected? And
Okay. So all the examples that they consider are quite simple. I mean, they're actual simple graphs. So they don't include self loops. They are connected. I think you could consider disconnected graphs. That shouldn't change anything. Yeah, but I think I mean, at least by writing my Laplacian like that, I am considering simple graphs. Okay, so the functor associates a Hilbert space. So I have to tell you what a Hilbert space is to a boundary subgraph. Let's see. So to say this is my y in, and this is my y out. So y in, y out, and I have to connect. Somehow they're connected. Doesn't matter how exactly. Okay, and this whole graph, this big graph, this is denoted by x. Okay, so this is a morphism between y in and y out in this graph cobordism category. And associated to this boundary subgraph, so my functor associates a Hilbert space. So the functor is denoted by hz. This is for the part of the functor that works on objects. This is for the part that works on morphisms. Okay, so you get Hilbert spaces. This is, and it's defined. This is quite usual in this formalism to take L2 functions on the configuration space on the boundary, and that's going to be the space of fields on the boundary. And well, in here, in our case, it's C0 y in. I've been also denoting it by F y in, and I will go back and forth between these two. And similarly for the out part, so this is h y out. This is L2 functions on C0 y out. Okay, and then this associated to this morphism, there's going to be a linear operator here, zx, right? I'm using z for the morphism part. And okay, so now I want to tell you about this zx, and this is an integral transform. So I have to tell you about first a particular subspace of fx, and then about a kernel, so an integral kernel for this integral operator. So this is integral. Transform. Okay, so the particular subspace, the affine subspace of this that I want to look at is denoted by this thing. So I pick 2 points. I'm calling them points because they are elements of my configuration space. So this is phi in is in f y in, and phi out is in f y out. And this space, this is, well, elements in fx, this is defined such that, you know, when you restrict your field to the boundaries, you have these guys. So phi restricted to y in is phi in, and similarly for phi out. Phi out is okay. So let me show you an example for how this affine subspace looks like. Okay, so let X be this very simple thing. So this is my Y in, this is my Y out, and this whole thing is X. Okay, and so Fx is gonna be three-dimensional, one dimension, each dimension is associated to each vertex, right? So this is Fx. And inside here, I have Fy in and Fy out. So this is Fy in, and this is Fy out, each of them one-dimensional. And then the rest, right? Which the rest here means Fx minus the union of these two boundary graphs. So Y in, union Y out. Okay, and the affine subspace, well, first you have to pick 2 points. 1 point here, this is phi out. This is probably not visible. Green. So you have phi in and you have phi out, right? You pick 2 points, and then you'll get a copy of this guy over here. So this is Fx phi in, phi out, which is the affine subspace that I've been talking about. Okay, so its restriction to the boundary, to the space of field on the boundary, is this point, right? But elsewhere it can be whatever you like it to be. Okay. And I would like to also have a measure on this space, and well, we'll denote that measure by this thing. So this is going to be used throughout the talk again, and this is, as we denoted things previously, V is in Vx minus Vy in union Y out. Yeah. Okay, so you just take away those that are not on the bound. You take away those that are on the boundary. Okay, and so in this example, this d phi, this is gonna be, in this example, just, well, if this is 1, 2, 3, it's gonna be dx2 over square root of 2 pi hy. Okay. And so now I want to tell you about the integral kernel for this integral transform. And so the integral kernel is going to be a function. I'll use the physicist notation. So this is the integral kernel for that operator. You see, like, it has 2 inputs. It goes from C0 Y out to R. And we define it, which is, this is the, well, I guess, a part of the genius of Feynman and Dirac, that you define it as a path integral, right? So you, at this particular, if this integral kernel at these 2 particular points, is phi in and phi out and phi in, is going to be, well, I'm going to integrate over the affine subspace that I defined with this restricted measure phi out. And I'm going to modify my action, which was on this whole graph X I defined earlier in the following way. By subtracting the parts corresponding to the boundary. Okay. So, so this thing, this will also be denoted by this will also be denoted by z x y. I'll tell you what y is. Phi y. Okay, so y is the union of y in and y out. We're just putting the boundary graphs and similarly the boundary fields together. Okay, and this thing is called it's the partition function of x relative to y. Okay, so it's just a notation at this point. So now using this kernel, yes.
Element of C0. Oh, I see. You've written here, so it's,
yeah, it goes from C0 out, C0 into R. So I want to define the integral transform in terms of the integral kernel. Okay, so let psi in be an element in this L2 space, in this Hilbert space. Then my Zx should take psi in to something in here, right, to an L2 function in here. So I'm going to denote that by psi out. I haven't told you what it is. But whatever it is, we should be able to evaluate it at a point phi out in here, right, because it's an L2 function. So, so this psi out evaluated at phi out is going to be d phi in and then okay, so you use this integral kernel and integrate out the in part in order to get something on the out part. Okay, so far, what I've done is defining the functor. So we know what h does, we know what z does, but now I have to show you that it's actually a functor, and for that, in particular, I want to show that compositions are mapped to compositions. Okay, so if you have, let me see how I denote this. If I have y1, y2, y3, so as before, we have, you know, this morphism x prime here and x double prime here. I want to show that this composition, right? And I was denoting this composition by x, right? So this whole thing, well, this composition was x, right? And what I want to show is that z corresponded to this morphism zx prime composed with zx double prime is going to be the same morphism that you get by taking the functor, putting x in it on the other side, right? So I want to show this this composition And in order to show this, it is enough to show the following gluing formula. So enough to show that if you take phi 3, so show it's enough to show this gluing formula for the integral kernels. Phi 2. Okay, so I want to show that this thing is equal to Zx phi 3 and phi 1. So phi 3 is the out state, and phi 1 is the in. Okay, so this is what I want to show. Yes. Yeah.
That X is isomorphism of Hilbert spaces.
Yes.
So previously, how were you defining that X?
Zx is defined like this. So this is Zx of psi in, right? This is this psi out. It's just a notation. I'm defining Zx like this in terms of that integral kernel that I define using this path integral, right? I'm saying what Zx does on this input L2 function at a point in this space. So that's, if you like, that's the definition of Zx as a linear operator of Hilbert spaces, where the Hilbert space is, it's an operator from this Hilbert space to this Hilbert space.
Previously, when you were recovering, like Zx was the number that you're recovering by doing what with it?
Okay, yeah, that's a particular, good question. So that was a particular example where I only had a graph X. I didn't have any boundary parts to it. So my boundary was the empty set, basically. So you can think of that. I'll look at this in a moment. Okay. Okay, so I want to show this. Right, and okay. So in order to show this, you expand this thing and this kernel and this kernel out using this formula, and you use Fubini's. Okay, so in order to show this, use Fubini. And the other thing that you need to do, so if you look at this, you'll see that you'll have an Sx prime part, Sx double prime part corresponding to this and this, and also some boundary pieces. And in particular, what's going to happen is that the y2 part of the first one, because you have y2 here, is going to combine with the y2 of the second one. And so somehow you have to relate this expanded out actions to the action. The only thing that you have here is Sx and the boundaries, right? So you'll use the other thing that you need to use Fubini together with this identity, that's Sx, or gluing of actions. At Sx on phi is Sx prime, phi prime. So phi prime is the restriction of phi on x prime, plus double prime. And because you can think that because you're double counting this graph y, or y2 in this example, you have to subtract that. So you have to subtract y2. Okay. And this last identity stands because it holds because we have the following identity for graphs, for Laplacians of graphs. So we have, so that last one using sorry, minus. Here, the dimensions don't match, but what you do is that you extend this by 0, so that all the matrices have the same dimension, same for this one. And seeing this one is easy, actually. So in order to see this, let me write delta x in the following form. So as a block matrix, where the first part is x prime minus y, the second part is y, and the third part is x double prime minus y. Okay, and similarly, you label the rows. And since x prime minus y and x double prime minus y are going to be disjoint, you get zeros here. So this guy looks at the degree matrix and the adjacency matrix, and if you're not connected, then well, it's going to be 0. These guys are 0, and this part is exactly delta x prime. So this part is delta x prime, and this part is delta x double prime, right? So I somehow managed to erase the blocks, right? So the bottom, this block is delta x double prime, that's delta x prime, and the middle block is delta y, right? So you add this up with zeros everywhere, together with this with zeros everywhere, but you're double counting this middle one, so you have to subtract that. Okay.
So this justifies the thing you just erased, which was the only thing that had no justification. Like the matrix elements of Zx and the argument of the exponential
Yes.
x minus 1/2 s of y.
Yes.
And there's a question right away, which is why should you subtract 1/2 of the action boundary fields?
Yes. Yes.
And somehow, because you want this functoriality, that just in a way it justifies why you have that expression. So if you didn't have that 1/2 s of y,
Exactly.
then this equality here that you need would not hold.
Well, this this one you mean? Yeah, this one wouldn't hold. Yeah, exactly. So you have
that is the key.
Yeah.
Fact that applies to reality.
exactly.
And yeah, and the problem is that z of x prime and z of x double prime are not completely independent. They have this common part, which is the 1, 2. So you're repairing this problem by defining the matrix elements have minus 1/2 s of the boundary.
Exactly. Yeah, it was here.
So in a way that indicates like that trick that you're using, this fact that you're incorporating functoriality by putting this boundary term
Into the, I guess, integral kernel. Yeah.
That fact, right? That seems to be like that's related to like a cocycle type condition.
Yeah.
It's like a cohomological fact that you're using. You're saying that I need this functoriality that's in a cocycle condition, and then it's almost like you're trivializing the cocycle and putting it into single matrix elements. But anyway,
Mhm.
You're just presenting a kind of solution to this problem, but I guess
Right.
if you really wanted to understand why those boundary terms are defined to be that way, you need to kind of approach this problem more cohomologically.
I see. I see.
But anyway, okay, let's go ahead.
Yep.
I just want to make sure that people understand what this issue is and why. Because actually, if you look at how, and it's unfortunate that it's raised.
I can write it.
Because it's the only thing that really highlights.
Yes, yes, definitely.
So if you think about that, right, that's an expression by itself, but this whole thing is a finite integral. And you know, it's an integral over a restricted space of fields where you're fixing the input field and the output field. And from the point of view of this finite integral, the action is being modified by just adding a constant. All that stuff, SYN, phi in, SY out, phi out, that's all just a single constant. And so from the point of view of this finite integral, it has no impact on, for example, the equations of motion, nothing. Phi in is constant, phi out is constant. So you're not doing much from the point of view of this finite integral. But you know, but it's having an impact on the functoriality.
Okay.
Sorry.
Yeah, no, that's okay. But there is a bit of a change to the equations of motion. I'll talk about it in a bit. So the equations of motion of this thing is a little bit different than the partition function in which you only have Sx.
Okay, but what I'm saying is that if you wanted to think of this as a field,
Mhm.
right, phi in and phi out are fixed.
That's true. Yeah.
And we have a space of fields where the boundary behavior, the boundary conditions are imposed. Right, so
Exactly. Yeah. That's the change.
the equations of motion, there would be no difference if you remove those constant terms.
Yes. 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 Because you already have the boundary conditions encoded into the space of
Yeah.
fields. Yes. Right.
I think some way you could see those traditional terms as sort of base transformation. You could use a different viewpoint in which instead of looking at L2 functions, you're looking at L2 functions with respect to the measure with density e to the minus 1 over h bar 1/2 times that s y in.
Yeah.
And that effectively is essentially a base transformation of the entire theory.
Yeah. I should talk to you about that.
Yeah.
Yeah. Definitely.
Because it's very reminiscent of something that I have done, so.
Okay.
It's very much, it's screaming at me that.
Yeah. Definitely. Yeah. Okay, so now I want to look at examples of this functor. The first example is what Walid asked. This is so example. It's the example of closed graphs. So in this case, you have the empty set and X to the empty set. The boundary is there is no bound, and it's empty. Okay, and the action here is you know, what we had before. Okay, and the partition function is again what we had before. And in particular, something to keep in mind is that because that was a Gaussian integral, what I wrote before, since this is a Gaussian integral and it's finite dimensional, you can actually evaluate it And because of the normalization that we have here, you get that this is determinant of kx, so minus 1/2. So, because my normalization included, so it has a square root of, yeah. Okay, and the other thing to keep in mind is that, so that we have this thing, so you can compute the moments of this Gaussian distribution, or you can call it Wick's lemma. And this tells you how to compute correlation functions. Okay, and this is, so by this lemma, the 2-point correlation function, this is 2-point correlation function is given in terms of the Green's operator. So in terms of the inverse of the kinetic operator. And when I write things like this means the particular entry of this matrix, right? Kx is a matrix, you can invert it and look at that particular entry. So we're gonna use this notation that Gx for Green's, I should use green. Okay. So yeah, we're gonna use these correlation functions to extract information about Green's functions. Yes. You have a question? Okay. Okay. And I can give you references for where to see, but there are a lot of references. So an example for a closed graph, there are so many examples, but we can look at this simple one. And well, Kx here is just going to be, okay, first of all, it's a 3x3 matrix. You need to write down the degree matrix, subtract the adjacency matrix, and add the mass terms. Okay, so when you do that, the first vertex has degree 1. 1 is connected to 2. 1 is not connected to 3. And it's going to be a symmetric matrix. So let me just do the upper triangular part. And okay, and so as I said, symmetric. Okay, so this is your Kx, and you can compute the determinant because it's a small matrix. And it's going to be m2, 1 plus m squared, 3 plus m squared. And note how adding this mass term moved us away from the 0 eigenvalue that every graph Laplacian has. So the lowest eigenvalue of a graph Laplacian is 0, always. Okay, and then Gx is certainly not enough space here.
Kx by shifting the graph of Laplacian by some scalar and then anything, right?
Yes, yeah, Kx is, yeah. Is that what the scalar you're referring to? Yeah.
Yeah, and like is it fairly invertible?
Yes, if you don't have 0 eigenvalues, I guess.
Oh, I see the graph of Laplacian always.
Yeah, it's 0 and then goes up. So yeah. Okay. I want to write out Gx.
One of the reasons you have this n squared is negative with that. It's a typical trick that you would use for any Riemannian manifolds, let's say. Because the Laplacian might have this. The Laplacian will usually have finite dimensional space of 0 eigenspace. So you can just add a positive number, and because it's a positive operator, all the other eigenvalues are positive. So
Okay. Examples get really, oh, I didn't write Gx, sorry. 1 second, so 1 over determinant. And then the entries. Okay, note that this is also a symmetric matrix. One. Then 1 plus, yeah, same thing as up there. And then complete. Okay, so this is your Green's operator. Yeah, the point that I want to make is that as your graph gets bigger, it gets really complicated, and you have to do certain tricks in order to actually find your Green's operator. Even for like a very simple graph like this with n vertices. You have to do some work. So maybe I'll come back to this example. Similarly for a circular graph. So the explicit formulas of all these guys are in the paper. Okay. Yes.
So this graph, like when we do normal, like functorial QFT, there's like a notion of there's a mountains with boundary.
Mhm.
But here, like you just gave this example previously of something with a boundary.
Yeah.
But here I'm interpreting it as a closed graph.
Yes. Well, I mean, this.
It's like new, right? This is kind of weird.
Let me see what you're saying
Like
exactly.
a cylinder, I can think
Yeah.
about it as something closed, my partition function.
Yes, because you have a codimension one. Your boundaries have codimension one in the I don't know, manifold cobordism category, right? But like in here, your objects and your morphisms, they have the same dimension in a sense. They're all graphs, right? So
it's like I can interpret this as a course between. Like,
yes, sure.
Or as a
Sure. Yes, you could think of it as something that goes, yeah.
This is boundary, you should think of it as structure, not as a property. You know, it's not that this graph has a boundary. No, it's that you decide what is the boundary. Okay.
Yeah, right.
I agree that it's strange, but actually, there's another point of view, unusual point of view, which is that instead of thinking of it as evaluating on the boundary or on corners or on points, let's say, you're really evaluating on a collar neighborhood, the collar neighborhood and so on. So in a way, some people actually think of quantum field theory as always being evaluated on an n-dimensional thing. It's just a question of what the topology of that n-dimensional thing is, whether it looks like a collar of some lower dimensional space or not.
Right.
Okay, that was our first example, closed graphs.
So these are the types of things that you want a gluing formula to obtain. You want a gluing formula that will tell us what this determinant of kx inverse is.
Exactly.
Or indeed what kx itself is, or what gx is.
Yes, mostly about determinants and Green's functions. Okay, so two, graph with a boundary, or the relative case. I mean, AKA, same thing. So, so now you have a distinguished subgraph, which is the boundary subgraph. So I'm going to think about this again, simple example. This is going to be y, and the whole thing is x. And associated to this, we define this restricted space of fields, this affine subspace, where you had Fy, the rest, and you picked a point in Fy called phi y, and you looked at all the fields that restrict to phi y on Fy, on y. So this is, and we use this notation. I forgot that, yeah. Okay, so we're doing this. And at this point, I want to focus on this affine subspace and I just want to look at this. So let's look at this guy. So on this guy, so on f x phi y, we had the relative partition function. And inside here, we had this modified action that Marco underlined. Okay, so this is the action that went into writing out this partition function. And so I want to look at the equations of motion of this in order to gather some tools for writing out the gluing formulas. Okay, so the equations of motion are going to be obtained by minimizing this action, and that corresponds to this being 0 on for all vertices in. So this denotes I've been already using it. This denotes vertices that are not in x, sorry, not in y, vertices in x that are not in y, right? Together with this boundary condition. So you get this by doing this kind of a variational calculus, for example. Okay, and so we want to solve this. Let me see. For this, I need to introduce another piece of notation, and that's for the Green's function, right? So x has a quadratic operator associated to it, kx, that I'm using here. So for example, we've seen examples of this. In this case, kx is 1 plus m squared. Okay, so this is kx. And I want to denote kx inverse as a block matrix. In the base, so I'm writing the vertices of x as a disjoint union of those vertices that are in y and those that are not. So again, this is the spaces y, and in this notation, I'm going to call this A, this is B, C, D. But I mean, this is a symmetric matrix, right? So this is symmetric, this is symmetric, and the transpose of this is the same as that guy. So we keep these things in mind, but I'm not going to write them. Okay, so in order to solve this, for a kx phi, well, it's 0 on anything that is on x minus y. So this is gotta look like something like this, right? For C in fy. Okay, so again, this is in the same basis, x minus y, y. It's 0 on x minus y. It's something on the boundary. I'm going to invert it. And, well, I'm going to use this block matrix decomposition, multiply in, and you get B, C, D, C. But I know what this field has to be on the boundary, because that's a condition. So, so by knowing that phi y and y is phi y, phi and y is phi y, I get that dc is phi y, and therefore c has to be the inverse phi y. Okay, so a solution to this equation is going to look like the following. This is a solution. Okay, right. So B inverse C and B inverse C? No, phi. Oh, sorry. Phi Y, phi Y. Yeah. Okay. And we're gonna call this. So let's look at this first. BD inverse. Well, D inverse goes from Fy to Fy, right? It's this particular block. And then B goes from Fy to Fx minus y because it's this particular block. So this composition goes from Fy to Fx minus y. And we will call this the extension operator and denote it by EYX. So this is, it's defined to be that. So you can think that it takes your boundary condition and drags it into the bulk, right? As a solution of this Dirichlet, this is called Dirichlet boundary conditions. This is a Dirichlet equation, an equation with Dirichlet boundary conditions. So it gives you, it drags it to a solution of this equation. Okay, and let me put it into the action, put the solution into the action. So Sx for the solution, so solution, well, you know, when you put it in there, you have 1/2 phi solution Kx phi solution. And it turns out to be just 1/2 phi d inverse phi y. So phi y d inverse phi y. Okay. And because of the way this equation looks like in comparison to the continuum model, which I have not described, this is a particular operator. So there's an analogy being drawn here, but also, you know, we are expressing the action using a quadratic operator here. So I guess this is a distinguished operator, and it's called the Dirichlet to Neumann operator. And it's denoted, again, it has this subscript yx. And this goes from Fy to Fy the same way that D does. And this is the definition of it. Okay, and I mean, in particular, it takes phi y, which is your Dirichlet boundary condition, to this C, which you could think of it as the Neumann boundary condition. But I mean, we don't have derivatives here, so it's a bit hard to see it. Okay, so let's also, that's the other piece of notation that I wanted to get to. And let me also introduce this other notation for Kx. So again, in terms of a block matrix, same kind of a thing, x minus y, y. I want to write it as this block matrix. So I'm putting hats everywhere. And I will call this block Kxy. So this block, A hat, is going to be Kxy. And Kxy goes from Fx minus y to itself. Okay, so I'm done looking at the equations of motion. Now I want to look at the relative partition function. So there's this this method of completing the square, which goes a very far way. I don't know. So let's see. So you can recall that this thing, this relative partition function, right? That's integral kernel that we wrote. This was fx phi y d phi y e minus 1 over h bar sx phi minus 1/2 sy phi y, right? And when you complete the square up there, right, you have a quadratic form here, you have a you have something else there that you're not really integrating, but by completing the square there, you can use the Gaussian integral formula that we used before to get this term. Okay, so this is the relative kinetic operator that I just defined. It's the top corner of kx. I'll just show you an example. I'll show you an example in a second. But that's not it, because I have to give you something that also depends on phi y. That's the leftover of that completing the square. And it's this. Okay. And that's minus 1/2 is also important. That is there. Okay. So this computation, I'm not doing it here. And it's not included in the paper, but I can go over it if you like. Okay. So this is something that I'll be using, but it's very long to write every time. Okay, so now I have to tell you about the correlation functions, because I told you about the partition function. And so the 1-point correlation function, this is given by, so this is the normalized, right? These are normalized. I might have written it wrong in the beginning. I didn't normalize it. Yeah, I should have. So this notation is for normalized. And this is gonna be EYX. So use the extension operator with respect to phi y. So these are relative. We're still in the relative case, right? X relative to y. So what this is gonna do is that, as we saw here, it takes phi y and it makes it to be a field in x minus y. So I can evaluate it at a vertex, at this vertex v1 that is in x minus y. Okay, and this is your 1-point correlation function. And then your, so this centered, I'll just write the 2 points, but you can write it for 2 times any positive integer. 2-point correlation function. Again, these are all normalized. So by centered, first I have to introduce this notation that when I write delta phi v, I mean phi v minus its 1-point correlation. So it's thought as, sorry, no, this is correct. So this is thought of as the deviation, fluctuation of field around with respect to its average. So if I don't have it here, I'm thinking that it's with respect to the, you know, ZX partition function that I wrote in the beginning. When I put this phi y, it's with respect to this partition function. So I should put it in there.
When you're computing, so 1-point correlation functions, we don't normally see those because
they're 0.
You're looking at fluctuations about 0, and you're evaluating the field at a point, and the average value of the field is going to be 0. So they're always just 0. But here you're averaging this quantity phi of v1, this observable, over all fields with a boundary condition imposed. So the boundary condition is fixed. And now you're only varying over fields that satisfy that boundary condition. And the interesting thing, as you would expect, what we should get is the value of the field in its lowest energy configuration, namely in the solution to the equation of motion. So this is consistent with the idea that you should, when you're doing computation, you always prefer to have a solution to the equation of motion. Normally, that's just zero, but in this case, it can't be zero since you're proposing the conjugate boundary.
Yes, yeah, exactly. Yeah. So yeah, the solutions to the equations of motion in the initial case is just zero. Like when, yeah, exactly. I mean, okay.
It's not so much that you're not using SX, right? You're still using the same action, SX. The point
Yes.
is you're averaging over a different space of fields, namely the ones that satisfy the space boundary. Again, repeating myself, that SY term that's added to the action is no effect.
Yes.
Should have no.
Usually not like this. If I'm interpreting correctly, this relative normalized correlation function is I put phi of v1 into that integral and I divide it by the integral of phi v1.
Yeah.
So adding in the sy by y, that was the other coefficient that we chose.
Exactly. Yeah, exactly.
Mhm.
Oh, I see what you're saying. You're saying normalized by Z without phi. Sorry, normalized by that Z with XY. Right. So that,
Oh,
that
yeah.
extra term cancels out.
Yes. That sounds about right.
Okay, sorry, so now you're
Yeah.
saying something about 2-point correlation.
2-point correlations because I'm interested in Green's functions. Okay, so right. So then I'm gonna write the usual. Again, Wick's lemma is gonna apply here. This is V1. Right. This is 2-point correlation function. By y, it is h bar. Again, I'm going to invert my quadratic operator, my kinetic operator, and look at these two, that entry of it. So it's h bar. And well, the same way that we did it for kx, this is the Green's operator, relative Green's operator, and we denote it by gxy. Okay, and so using this formula, you can compute the non-centered correlation functions, of course, as well. Should I finish at 3 or should I go?
So KXY, did you define it?
Yes.
It was the A hat, right?
Yes. It's this upper corner.
And right, so okay.
Yeah, do I finish at 3?
You're kind of you're expressing the Green's operator. Oh, I'm sorry. So it's KXY inverse. So it's
Yeah, it doesn't show up as any of the blocks that I've talked about yet so far.
But in any case, the way that you obtain it, you need to consider this centered 2-point function.
Exactly.
Normally, we don't have this issue because the average is 0. So centered is not necessary. Okay, yeah.
So what time should I finish?
Well, how much more do you have?
I have a good amount left.
Yeah, what fraction are you?
Like I'm gonna state the theorem and then there are proofs. So there's
Are you halfway through the talk, or are you 2/3 of the way?
2/3, 2/3. Oh, half. It's half.
Half.
Yeah.
Well,
Let's see how it goes and see where we're at.
Oh, so it's 2:45. Okay. So yeah, because I can jump. Okay, what should I do?
The thing is that I would be happy to have you continue, but the problem is that we're going to talk next week.
Yes, yeah. So
we don't really have the opportunity to have a second talk.
right.
On the other hand, we have other things today, so is there a good place to stop? Like, can you take 15 minutes? And
Yes.
Do something?
Yes. Okay, great. Thank you.
I mean, it's very good. You're doing well. I like that. The speed is good.
Okay, thank you. Okay, so yeah, so there's a simple computation that we can do here in order to get the non-centered two-point correlation function. Okay, and when you do it, you see that it's V1, V2 plus, well, something in terms of these extension operators. Y. Right, this is a number times another number. Okay, and that's again the entry, the V1, V2 entry of GXY. So this is useful in the proof. And so I can show you an example. Maybe, I think this would be helpful. So this is Y. This is X. The whole thing is X. And KX, I wrote it before, it's 1 plus m squared minus 1 minus 1 plus m squared. Okay. And I have this block decomposition, X minus Y. So this is vertex 1, this is vertex 2, X minus Y, and the Y part. So this is KXY. GXY is the inverse of this. It's a number, so the inverse of a number is also a number. It's this thing. And okay. And then you can take the full inverse of KX. I'm not going to do that. In order to find the dn. So maybe I should do that. So let me take the KX inverse, and it's a 2 by 2 matrix. We can do it. I'm going to look at here. And then it's 1. Okay. And dn, recall that that's this part. It's that part inverse. So we were denoting this by A, B, C, D, and dn. How's this color? Visible? Okay. And this is the inverse of that. So it's, but I mean, you have this determinant as well. So you should write m squared plus m squared. Right. And the extension operator, well, that's BD inverse. B is this one, D is this one. But throughout doing this computation, this determinant is going to get canceled. So EYX is sorry, what did I say? E, yeah, 1 over 1 plus m squared. And again, it makes sense that this is also a number because y is one dimension, like fy is one dimensional, fx minus y is also one dimension. So okay. And you can also write out the relative partition function. We have it there. And same as before, writing out bigger graphs gets complicated very quickly. So let me do the last example, which has the main theorem in it. And the last example is cutting a closed graph into two subgraphs, right? So you have a big graph and you have X. You have this graph X, and X is obtained as the gluing of X prime and X double prime through a common subgraph, the interface Y. Okay, so X is this. You know, you can draw more complicated stuff too. And so now I'm in a position to tell you about the gluing theorem. So I'll state it. First, it's about the gluing of Green's functions. So it's Gx, right? This is the Green's function associated to this graph X. And on the right-hand side, I would like to have something in terms of the relative Green's functions. So, well, it's the relative Green's function. Okay, but I should tell you where these vertices are in order to write out the right-hand side. Here, I'm thinking that, so in this case, I'm thinking that V1, where should I write it? So V1 and V2 are both in X prime. So it does matter where your V1 is and where your V2 is. Are they both here? I mean, it could be like these two, or one is here and one is over there. Okay, so you would use like different things. Plus sum over U1, U2 in Y, EY X prime, V1, U1, D and inverse, U1, U2, and then EYX, V2, U2. Okay, so you can think that you go from X prime to Y, you do some summation over all the vertices in Y, and you come back because you have two vertices. Okay. And if you had one vertex in X prime and one vertex in Y prime, you would not have this term and you would only have this term. But here, so these are both X prime. When it's one from X prime, one to X double prime, then one of these guys is going to be X prime, the other one is going to be X double prime. Okay. And I should tell you what this dn operator is. I have not defined it. So where yx, this is dn. This is the total dn operator. Yx double prime minus ky. Okay, and so far we've been talking about this kind of decomposition of vertices in terms of x prime minus y, x double prime minus y, and y. And here we are not doing that. So I have to tell you how to extend things like this to the case where one of these guys is going to be on y, because we don't know that as of now. So and assume, so, and you should assume by convention that gx prime y of v1, v2 is going to be 0 if any of them is in, if either of them is in y. So if one of the legs is in y, this is going to evaluate to 0. And also, I have to tell you how to extend this to y and e y x prime y x prime of uv is going to be delta uv. So it's going to be 1 if this is the same thing and 0 else otherwise. This is for when they are in y, of course. Right? Because usually one leg is in y and one leg is in x minus y. But now it could be the case that both are in y, and then I have to tell you what the value is. So that's covering that. This is part A of the gluing theorem. Gluing theorem. And part B is about the determinants. And of course, this thing that I wrote, this works as well the same way if both legs were in x double prime. So same equation holds. Thank you. Okay. That, and again, we only have vertex 2 in Y, and then you have EY X double prime, and you have 2, 3. Okay, and you can just plug numbers in here, but since I didn't do the example, I think I didn't do the example for X being a 3 vertex guy. I don't remember actually if I did it or not. But anyways, if I did it, then you can check that they agree. If not, that's okay. And similarly, you can compute a determinant. Right, I did that. I remember the determinant at least. So let me write the determinant, and that's going to be where I stop. The determinant of Kx, right? X being this thing, Kx is a 3 by 3 matrix. And this is where I pointed out that the determinant is not, so determinant of Kx is m squared plus 1, m squared plus 3. Okay, so let's see if that's the case. Determinant of Kx prime y is 1 plus m squared. Determinant of Kx double prime y, same thing. And determinant of the Dirichlet-Neumann operator is just, sorry, I'm pointing at this, but this is not it. It's that thing. And when you actually do the computation, you see that it's equal to m squared, 3 plus m squared, and we have cancellations. Okay. So I will not do the proof then. Okay. Yeah.
Obvious question. Do you know how to like maybe give ideas about how to extend it to non-free scalar? Or I guess in the paper you said they do non-free scalar theory.
Yes.
Well, what if I want like gauge theory? Thought about how to incorporate other kinds of things.
Yes, I have, but I don't have a clear picture yet. Yeah, so it seems like you would have to, I think they also suggest this in the outlook part of the paper, that you would need to include fields that are not just zero cochains, right? So higher cochains, but maybe like another paper that does something closer to that is the work by Rishitikin and Bertman.
I guess the point, I mean, I understand the point that the proof of this one formula is very important,
Yes.
because it's basically saying, it's basically kind of, you know, the idea is supposed to be that this determinant of this global thing is splitting. I mean, there's 2 formulas, one of them for the determinant
Yes.
and expressing the determinant of the Lassian of the whole graph as a product of determinants of smaller graphs.
Yes.
And then there's this other thing about the Green's function. And so I guess the point is that to prove these things using quantum field theory
Yes.
would mean that you express these things as observables.
Exactly.
The first one, we know what it is. It's the partition function itself. That's what.
Yeah. Yeah. The first one just follows from that gluing formula that we wrote in the beginning. Zx prime y.
Fact that you have a path integral description for the determinant, and the fact that you can take that integral and decompose it into smaller pieces, that's what gives rise to that determinant formula.
Exactly.
And the same, and then this idea of the Green's function, then we need to say, well, okay, what's the Green's function from the point of view of the quantum field theory? It's a 2-point function.
Exactly.
And so then you can cheat the two-point function by the path integral, and you use the decomposition of the integral there.
Yes.
So this is, that's the prototype of any such results.
Exactly.
You can, so in that way, you get Riemannian geometry formulas, right? You get these facts about Riemannian geometry, about how the determinant of the Laplacian breaks up into parts of your manifold, or how the Green's function of a Laplacian operator breaks up. Right? You get facts about Riemannian geometry from the path integral description. These observables.
Yeah.
And you know, you can take that approach, that idea, all the way to, for example, determining, you know, the Kontsevich formula for the star product of the Poisson manifold by expressing it as an observable in quantum field theory, written in terms of the path integral formula and expanding that up. So it's a very powerful technique that here they're using to obtain these graph environments. Next question. As long as you don't preface your question by describing, just ask the question. Ask it.
Like these guys, the fact that you're able to do build in these kinds of analogs of like the Laplacian and Green function, can you do some kind of repository in this setting?
That's ideal. Yes. They don't talk about that, but you would like to do something like that. Yes. Can you do? I don't know. I haven't
What do you
tried
mean?
it. Yeah.
What's your question?
Like the fact that you can build analogs of these operators like the Laplacian, and like can you do something about like some decomposition of the
Well, you have Laplacian.
right?
What is the, in your opinion, what is artificial? What is of what?
Of like some space of form and then like making a descent to some kind of homology. I guess homology doesn't happen here.
Why not? Look at the beginning of the talk.
Yeah. You have this.
If you want. You have an operator, D, you have the adjoint, you find the Laplacian. The Laplacian has eigenvalues, some of them are zero, some of them not. It's no different. It's exactly the same.
Can you get like this bi-grading on your homology?
Bi-grading.
Right. There's a lot.
What bi-grading are you talking about? Apologize. It's good. Learn something.
Thank you.